economy and reduce emissions. First, we'll review the basics of how an engine works and some basic engine terminology. An internal combustion engine needs air and fuel to function. The more efficiently an engine breathes, the more efficiently it will produce power. Now we'll look at the basic components of an engine. The main components of the engine are the engine block and cylinder head. The internal components of an engine include cylinders, the crankshaft, connecting rods, pistons, spark plugs, fuel injectors, intake and exhaust valves, camshafts, and a timing chain or belt. As the piston moves on its first downward stroke, the intake valve opens to allow a mixture of air and fuel to fill the combustion chamber. This is called the intake stroke. Next, the intake valve closes and the piston moves on an upward stroke that compresses the air-fuel mixture. The compression of the air-fuel mixture will make it combust with greater force than if it were uncompressed. This is called the compression stroke. Third, the spark plug ignites the air-fuel mixture, causing it to burn explosively, which forces the piston into another downward stroke. This is called the power stroke. The fourth stroke is the exhaust stroke. As the piston begins its second upward stroke, the exhaust valve opens and the burned air-fuel mixture is forced out of the combustion chamber through the exhaust valves. Two terms you may be asked to explain to customers are the engine's compression ratio and displacement. Compression ratio is the ratio between the total volume of a combustion chamber and cylinder when the piston is at the bottom of its stroke and when the piston is at the top of its stroke. In this example, the compression ratio is 10:1. Higher compression ratios produce more power but require higher octane fuel than engines with lower compression ratios. Engine displacement is how the internal size of an engine is described. It's measured as the cylinder bore times the length of the piston stroke. This is multiplied by the total number of cylinders and is usually expressed in liters or cubic centimeters. For example, a 2.4-liter four-cylinder engine has a total displacement when adding together all four cylinders of 2.4 liters. The number of valves that engines have varies. Older engines tend to have one intake and one exhaust valve. Some engines have two intake and one exhaust valve. Most high-performance engines use two intake and two exhaust valves. The opening and closing of the valves is performed by the camshaft. Some engines use one camshaft with rocker arms and/or push rods actuating all of the valves. If the camshaft is above the valves, it's called a single overhead camshaft or SOHC engine. When an engine uses a separate camshaft for the intake and exhaust valves mounted above the valves, this design is called double overhead camshafts or DOHC. All Toyota engines use double overhead camshafts. Most four-cylinder engines, including all Toyota four-cylinder engines, are an inline design. Engines with more than four cylinders typically have the cylinders arranged in a V configuration. All Toyota 6- and 8-cylinder engines are V-type engines. Now let's look at technologies Toyota uses in its engines to enhance power output, fuel economy, and emissions control. The more efficiently an engine breathes, the more efficiently it will produce power. Toyota engines incorporate a number of features and components that are designed to help the engine breathe more efficiently. An acoustic control induction system, or ACIS, automatically varies the length of the runners in the intake manifold to maximize the airflow into the engine and to provide more usable power throughout the entire RPM range. At low speeds, ACIS directs intake airflow through a long intake runner in order to produce ample low-end power and torque. Think of this as taking deep breaths while lifting a heavy object. At high engine speeds, ACIS directs the air through a short intake runner in order to generate more horsepower. Think of this as taking quick, short breaths while running. Some manufacturers utilize a single overhead or SOHC engine. All Toyotas feature double overhead cam or DOHC engines that allow optimum placement of the valves. Benefits of a DOHC design includes enhanced power output, fuel economy, and emissions control. Since the power of an engine is determined by how much air and fuel can be burned in a given period of time, Toyota uses 4 valves per cylinder instead of 2 or 3. This arrangement improves the intake and exhaust performance of the engine over other valve configurations. A 24-valve engine would be a 6-cylinder engine with 4 valves per cylinder. Variable valve timing with intelligence, or VVT-I, is one reason why Toyota cars and trucks develop horsepower and torque across a broad RPM range or power band. A computerized system changes the intake valve timing to optimize the engine's breathing depending on the conditions. Without VVT-I, valve timing is fixed no matter how fast the engine is turning. As a result, an engine that works well at high speeds won't perform as well at low speed and vice versa. With VVT-I, intake valve timing is constantly adjusted, enabling the engine to perform well over a wide range of speeds. For an even greater range of valve control, some Toyota engines use dual independent VVT-I, which controls both the intake and exhaust camshafts independently of each other. This provides an even greater range of valve control. Double overhead camshafts makes it possible to independently control the intake and exhaust valves. This results in enhanced power and torque delivery and greater fuel economy throughout the vehicle's power band. A dual-path exhaust system works somewhat like ACIS, except ACIS maximizes airflow into the engine, while the dual-path exhaust maximizes exhaust flow out of the engine. A second path or chamber opens in the exhaust system at higher RPM to help evacuate the higher volume of exhaust, resulting in better breathing with less back pressure.